is a form of energy. Temperature shows how hot a thing is. In other words, heat refers to the quantity of energy present in a substance, while temperature refers to its intensity, that is, the degree of hotness. For example, a glass of boiling water has the same temperature as a large can full of boiling water. Even though the temperature of water in the two vessels is the same, the glass does not possess as much heat as the can. Subtraction or addition of heat is necessary to lower or raise the temperature of a substance. Besides, differences in the temperature determine the direction of heat flow from one body to another. As we all know, heat moves from a hotter body to a colder body. Therefore, temperature has been defined as the property which determines whether heat will flow out of or into an object when in contact with one another. After going through this module, you will be able to understand the process of heat energy transfer, understand heating and cooling of the atmosphere, understand the controls of temperature. Heat energy is transmitted by the process of radiation, conduction and convection. Each of the three mechanisms of heat transfer has an important role in affecting weather changes. Radiation. Radiation is the process of transmission of energy from one body to another without the aid of material medium, solid, liquid or gas. Through the process of transfer of heat, there is no warming of the medium. It is by this process that most of the energy is transferred through space from the sun to the earth. The transmission takes place along straight lines. The process of transfer by radiation is similar to wave motion, and a wide range of wavelengths is possible. Conduction. Conduction is the process of heat transfer through matter by molecular activity. In this process, heat is transferred from one part of the body to another or between two objects touching each other. Conduction occurs through molecular movement. Heat flows from the warmer to the colder part of the body so that the temperatures between them are equalized. The ability of the substances to conduct heat varies in direct proportion to the heat conductivity of the substance. Thus, metals are good conductors while air is a very poor conductor of heat. Besides, so long as the differences in the temperature between any two bodies in contact with each other is large enough, the conduction of heat from the warmer to the colder body proceeds at a faster rate. As soon as the difference is reduced, the process of heat transfer is slowed down. Therefore, for the transmission of energy through this process, it is essential that the difference between the temperature between the touching bodies is large enough. Convection. Convection is the process of transfer of heat through movement of mass or substance from one place to another. Thus, it involves a transfer of heat by means of mass motions of the medium through which the heat is transferred. Convection is possible only in gases or fluids, for they alone have internal mass motions. In solid substances, this type of heat transfer is impossible. In this process, the moving substances transport the heat acquired by conduction previously. The atmosphere is heated or cooled by the following process which have been briefly discussed here. Firstly, partial absorption of the solar radiation by the atmosphere. Secondly, conduction. Thirdly, terrestrial radiation. Fourthly, convection and advection. Fifth, latent heat of condensation. Sixth, expansion and compression of the air. Partial absorption of solar radiation. As we know, the atmosphere is not heated directly by the sun's rays passing through it. Even then, the dust particles and water vapor present in the lower layers of the atmosphere directly absorb about 10% of the incoming solar radiation. About 50% of this absorption occurs in the lower 2 kilometers of the air, where most of the water vapor is found. However, the process of absorption is not very effective in raising the surface to air temperature. That is why even on a clear sunny day, the temperature near the surface remains low. In winter, people enjoy the warmth of sunshine by sitting close to the side of a wall of their houses, exposed to the sun, because the short-wave incoming solar radiation is being converted into long-wave terrestrial energy. Conduction. Conduction is a slow process of heat transfer as regards warming of the atmosphere. Since air is a very poor conductor of heat, the conduction process affects only the lowermost layers of the air closest to the Earth's surface. As a means of heat transfer for the atmosphere as a whole, the conduction is least important and can be neglected when considering a majority of meteorological phenomena. Terrestrial radiation. It has already been pointed out in an earlier chapter that about 2/3 of the radiant solar energy reaches the Earth's surface directly or indirectly in the form of short-wave electromagnetic waves, where it is converted into terrestrial heat by the surface of Earth. The Earth radiates heat as a black body, while the radiation from the atmosphere is selective. Thus, most of the atmospheric gases, especially carbon dioxide and water vapor, that are almost transparent to the short-wave solar radiation and are able to absorb only about 19% of it. Absorb about 85% of the terrestrial radiation of long-wave or infrared radiation in this form. Thus, it is clear that the atmosphere receives a larger part of its energy supply from the Earth and not directly from the Sun. Since the atmosphere is about almost transparent to most of the solar radiation and absorbs a large part of the terrestrial radiation, it acts to conserve the heat energy of the Earth. This conservation is called the greenhouse effect. Water vapor, carbon dioxide, dust particles and ozone are directly involved in the process of absorption of terrestrial radiation. But water vapor is the most important. It is on account of this that in the arid zones characterized by the minimum amount of water vapor present in the atmosphere, nights are cooler because of the Earth's radiation of the heat. On the contrary, even in the long winter nights when there is thick cover of clouds, the temperatures remain relatively higher because of the absorption of long wave terrestrial radiation by the clouds. Convection and advection. Since the atmosphere is a gaseous medium, convection is the most significant mechanism of heat transfer. Heat gained by the layers of air at or near the Earth's surface from radiation or conduction is usually transferred to the upper layers of the atmosphere by the process of convection. Transfer of heat by convection takes place in two forms. Firstly, sensible heat content of the air, which is transferred directly by the rising and the mixing of the heated air, and secondly, latent heat, which is the indirect form of energy transfer by convection. When the condensation in the free atmosphere takes place, the latent heat of evaporation is released and made available to the air. This is known as the latent heat of condensation. Latent heat of condensation. There is no doubt that the atmosphere receives a large percentage of its total heat energy from the long wave terrestrial radiation, conduction and convection. But in the heating and cooling of the atmosphere, the latent heat of evaporation as well as the latent heat of condensation also play a significant role. The latent heat of condensation is made available to different layers of the atmosphere by the process of evaporation taking place at the surfaces of the oceans, humid ground, and natural vegetation. Oceans with their extensive water surfaces exposed to the sun are the most important sources for latent heat of evaporation. It is estimated that half of the insolation received at the ocean surfaces is consumed in the evaporation of the surface water because the process of evaporation needs a certain amount of energy. This transformed solar energy is thus contained in the air in potential form. When water vapor is condensed, the latent energy is again released into the atmosphere and is used in heating it. The released energy is known as latent heat of condensation. It may be pointed out that the latent energy of evaporation does not raise the temperature of the water vapor. When condensation or sublimation takes place, the water vapor is converted into solid or liquid form. Then the latent heat is released and it raises the temperature of the air. Expansion and compression of the air. Whenever air moves upward, it passes through regions of successively lower pressure. Consequently, the rising air expands and cools adiabatically. In the same way as the air descends, it comes under increasingly higher pressures, so it compresses and is heated. These temperature changes caused by the change of pressure alone that the rising or falling air is subjected to are called adiabatic temperature changes. As a process leading to adiabatic cooling, it is common whenever the Earth's surface is warmer than the air above. Thus, the temperature changes brought about in the air aloft simply due to the changes in the air pressure are very important in the heating or cooling of the atmosphere. The controls of temperature include those factors that bring about spatial variations in the temperature. The following are some of the more important factors which determine the temperature of a particular place on the Earth's surface: latitude, altitude, distribution of land and water, ocean currents, prevailing winds, cloudiness, mountain barriers, nature of the surface, relief, and convection and turbulence. Latitude. Intensity of insolation depends on the latitude. Since insolation is a prime factor in determining the temperature of the air, it is but natural the temperatures would vary with the latitude. Thus, the temperature of an atmosphere at a particular place near the Earth's surface is a function of the insolation received at that location. The total insolation is more intense in the low than in the higher latitudes. As we move away from the equator to the poleward, the mean annual temperatures show lower values. The most important causes for variation in the amount of solar energy reaching the Earth are the seasonal changes in the angle at which sun's rays strike the Earth's surface and in the varying lengths of the day. There is no doubt that all of the factors, latitude is the most important. This is proved by the general east to west trend of the isotherms drawn on maps showing the mean annual temperature distribution on the Earth. However, the irregularities of the isotherms do suggest the influence of other factors on the distribution of temperature on the surface of Earth. Altitude. We know that temperature decreases with increasing altitudes from the Earth's surface. This vertical decrease in temperature or the atmosphere is limited to the troposphere only, in which the normal lapse rate is about 6.5 degrees Celsius per kilometer. Since the direct source of atmospheric heat lies at the surface of the Earth, the higher we ascend in the atmosphere, the lower the temperatures are. The second factor which causes the lowering of the temperature with the elevation is the fact that the lower layers of the air at or near the surface are denser and contain more water vapor, more water particles and more dust particles than the upper air. Since these substances absorb a large amount of terrestrial radiation, the lower part of the atmosphere has higher temperatures than the less dense and cleaner upper part. The permanent snow caps on the high mountains, even in the low latitudes, indicate the decrease of the temperature with the altitude. It shows the effect of altitude on temperature. Mount Kenya, 5,199 meters high, even though located at the equator, is cold enough to have a permanent snow cover in its upper parts. Distribution of land and water. Land and water surfaces react differently to the incoming solar radiation. That is why different surfaces such as land, water or ice heat up and cool down differently. For example, land surface is heated more quickly and to a greater extent than the water surface when subjected to an equal amount of insolation, and it also cools more rapidly. Because of the great contrast between land and water surfaces, their heating capacity, the atmosphere varies. This arises from the fact that whereas water tends to store the heat it receives quickly, land quickly returns it to the atmosphere. Variations in the air temperatures, therefore, are much greater over the land than over the water. It is the differential heating of the land and water that accounts for the distinct types of marine and continental types of climates found on the surface of the Earth. The factors which account for the differential heating of the land and water, since water is essentially transparent, it allows some heat and light energy to penetrate to a depth of several meters. Land surfaces, on the contrary, are opaque, so that there is a greater concentration of insulation in a thin layer of soil and rock within the consequent greater heating. Because the solar energy on a square meter of ground is distributed over such small mass of material, it naturally causes a greater temperature increase than would be caused by the same amount of insulation falling on the water surface. The specific heat of water is much higher than that of land. In other words, heat is required to raise the temperature of 1 gram of water by 1 degree Celsius than the same amount of land. For water, the specific heat is one which is among the highest of all such values. Specific heat is almost 3 times greater for water than it is for land. Thus, a given quantity of incoming solar radiation would increase land temperatures more than the temperature of an equal mass of water. Similarly, for a temperature decrease of 1 degree Celsius of mass of water gives off much more heat than does the same mass of the land. Water, being fluid, is highly mobile. Heat in its redistributed form mainly through turbulence, ocean waves, tides and currents aided by the convection distribute the absorbed solar energy at greater depths. Besides, the cool and heavy water of the surface at night sinks and is replaced by warm water from the below. Hence, a large mass of water must be cooled before the temperatures of the surface layers are reduced. That is why sea temperatures change relatively little from summer to winter. In other words, the sea surfaces show little seasonal variations. Thus, the temperatures of the water surfaces tend to fluctuate more slowly than those of the land surface. Land surfaces, on the other hand, are static. Heat in solid earth is distributed by slow process of conduction. The vertical distribution of the heat in land is such a slow going process that diurnal temperature changes are very small, below a depth of 10 centimeters. On land, therefore, only a thin layer is heated to much higher temperatures during the summer. During the winter, the same shallow layer cools rapidly, producing large diurnal and annual temperature ranges on the land surfaces. Evaporation from the water bodies is greater than that from the land surfaces. The evaporation process consumes a large amount of solar energy in the conversion of liquid water to water vapor without any increase in the temperature. Evaporation process is more effective in moderating the temperature in all the large bodies of water during summer. However, it is only a minor factor. But on the land surface, evaporation takes place only from wet ground, and that too during the period of sunshine. It is, however, interesting to note that in the wet tropics, evaporation from the continents is greater than that from the oceans. Ocean currents. Ocean currents move from one place to another in order to equalize temperatures. There are large movements of ocean water, usually from a place of warm temperatures to one of colder temperatures or vice versa. In all the oceans, cold currents move from the polar regions equatorward and warm currents from the equatorial regions to poleward. The effects of ocean currents upon the temperatures of the adjacent land areas are variable. The warm currents raise the temperatures of the nearby coastal regions slightly above the mean values. Similarly, the cold ocean currents tend to lower down the temperatures of the adjacent land areas. The North Atlantic drift offers a typical example of warming effect of the ocean currents on the adjoining land masses. It is a well-known fact that the climate of the northwestern Europe is modified to a large extent by the warmer ocean currents of the North Atlantic. Prevailing winds. It is obvious that neither oceans nor ocean currents can exert maximum influence upon the temperatures unless the direction of the prevailing winds is such as to carry the moderating effects of the oceans to the adjacent land. On the contrary, offshore winds take the effects of warm or cold currents away from the coastal regions. Cloudiness. The atmospheric depletion of insolation is relatively less in those regions that have clear and cloudless skies. Outing the summer season, the subtropical deserts are much warmer than the equatorial regions, especially during the daytime. It is mainly due to the fact that near the equator, thick cover of the afternoon clouds does not allow the incoming solar radiation to reach the Earth's surface without a certain percentage of it being absorbed by the clouds. In humid regions, because of the presence of a large amount of water vapor in the atmosphere, nights are relatively warmer than those in the arid regions. Mountain barriers. Landform barriers, particularly high mountain ranges, exert significant influence on the temperature of a place. Mountain ranges block the movement of the air from one place to another and thus control the weather and climate of a locality. Nature of the surface. The effect of the nature of surface and its color on the distribution of insolation has been discussed in an earlier chapter. Different kinds of surfaces reflect different amounts of incoming solar radiation falling thereon. Dark colored substances absorb more insolation than the light colored ones. Snow covered surfaces reflect a large part of the incident solar radiation which is not available for heating the layers of the air lying adjacent to the surface. That is why the temperatures over snow covered ground remain low even during the daylight hours. Relief. On a local scale, even differences in the elevation of the land and its slope strikingly control the temperatures. Although it is true that high elevations receive a larger amount of insolation under the cloudless skies than locations at or near the surface level, sea level, there is undoubtedly greater net loss of terrestrial radiation at higher elevations. Besides, relief also controls the quantity of insolation and the duration of direct sunlight. At certain hours of the day, places located in the valleys and on the slopes do not get direct sunlight. In the northern hemisphere, the southward facing slopes are exposed to the sun for longer period of time and are in receipt of greater amount of insolation than the northward slopes. Convection and turbulence. Intense daytime heating of the surface produces convection currents in the atmosphere which transport heat to the upper layers. Thus, the convection currents and eddy motions moderate the temperatures of a particular place. In winter, streams of air cross the mountain barriers and descend on the leeward side. In the process, they get warmed up by the compression and thus the air temperature is raised. Fawn and Chinook are such local winds as across the Alps and the Rockies respectively during winter and bring about unprecedented rise in the temperatures of the localities affected by them. In brief, it may be stated that the temperature of a particular place is affected not only by the latitude but also by a number of other general and local factors. Besides, the relationship between the earth and the sun as well as the complex process of heat exchange between the earth and its atmosphere also exert a collective influence on the spatial variations of